All right, let's talk about some of the basics of linear regression. So I'm going to draw this familiar pattern that we've seen in the last couple of videos here and in the chapter. So let's say I have a data set that's represented as these green data points where they're plotted in XY pairs, and my goal is to draw a line that best fits this data set. Now, the idea of linear regression, actually let me broaden this up a bit. Let's get a little bit wider berth here. The idea of linear regression is that I'm going to draw a line that best fits the data set in a way that the line represents a regression or a central point or an average of the data. And that average, I'm sorry, to be more specific, that average is found by regressing from the data, right? So it's going to try to be as far away from the dots on the bottom as it is from the dots on the top, right? And the basic idea with a linear model is that you have two values that you need to find. So these two values are represented by m, which is the slope of the line, and b, which is the intercept of the line. In this really basic case, we only have one input, right? And that one input is x. Now, I'll mention it again later, but linear regression can be expanded to as many inputs as you want, so it's just very easy to represent this concept in two-dimensional space. But it could very easily be three-dimensional, four-dimensional, five-dimensional space. You could have as many of these x values as you wanted to. And then that'll actually be much easier to implement when we get into the scikit-learn package. We won't build that from scratch, but just take my word for it as we're understanding these concepts. Okay, so how to do this? So how to find the best fit line? The idea is that we need to get to a point to where we can answer the question: what is the intercept and what is the slope that best fits this set of data? So I want to go back to the concept that you looked up and you learned in the last section called sum of squared errors and gradient descent. So you remember the concept of gradient descent was that you have some convex function, and we're going to have some starting point, right? Like up at the top, some arbitrary starting point. This starting point for us now will have some some slope, some m and b. That will be wrong, right? That will be quite wrong. And the idea is we're gonna change these. We're gonna change these values of m and b to the point where we're gonna improve until we get to the best possible cost associated with this value. So the way that we're gonna build this cost function is through sum of squared errors, and I'm gonna show you how gradient descent can be applied to then do this improve process. And then we'll not only show you here mechanically how it works mathematically, I'll also show you in the next section a video about how we would program it. Okay, so sum of squared errors, if you remember from your practice, is the sum of the difference, and in this case is our function of x for each data point x sub I minus the actual observation y sub I squared, right? And if I do this over y equals 1 to n, and n is all of the data observations, then this gives me my cost, right? So my cost is the sum of the squared errors. Now, because it's squared, this squared gives us an opportunity to use convex optimization routines, and gradient descent is the most common. You'll see it in even the most advanced quantitative modeling. But demonstrating it here, we can do something that's really powerful. The way gradient descent works is it's set up by this basic function. The idea is that you have two different parameters, and in our case we have a beta, and we'll call this k plus 1, and then we have our slope m, k plus 1, and k plus 1, beta, and m plus 1 are simply equal to the beta of k, or the m of k, minus some learning rate alpha times the derivative of the function with beta k. So the derivative of the function with m of k. Right, and so I'm not going to walk you through how to actually calculate these derivatives, but the idea is that if you can calculate the derivative of the function that's over here, then we have a really simple formula that allows us to iterate down this slope, right? So now you can see that for each step is represented by that iteration until we get to some point to where the difference between these two steps in iteration, so going from k to k plus 1 for each of these two parameters in our functions, gets to be so small that we're happy, that we know that we're close to the minimum amount of cost. So the way this works out for these two applications here is pretty straightforward. So I won't run you through, like I mentioned, I won't run you through the mechanics, but it will look like this specifically for linear regression. So k plus 1, which represents one iteration in front of k, and m plus 1. These are both equal to a little better alpha there, and then this is the functional representation. I equals 1 to n function of x sub I minus yi, and this is the sum of, oh, that was ugly. Sum of I equals 1 to n f x sub I minus y sub I, these are also sub I, times x sub I. Okay, and the idea is that I can apply both of these recursively until I get to the point to where I'm happy with these two values. All right, this will make, if this was super confusing to you, don't worry about it. This will make a lot more sense in the next video when we do it programmatically, show you how this will actually look in a setting with Python that will hopefully connect some of the dots for you. All right, I'll see you over there.